Next, let us look at complex vectors, and there it is completely enough to look at vectors with just two components, such as these ones here. And now I'm going to denote them with Greek letters. Let's call them psi and phi. So first let's look at the length of these complex vectors. And for this we now use our scalar product. So I'm going to denote it like this. And now we have to take the absolute value squares of these numbers. So that would be 16 plus 4 coming from this real and this imaginary part here, plus 4 plus 1 coming from this real and this imaginary part. So that's 25, that's 5 squared. And for 5, we have just again a 4, 2 2's, and a 1. So that will also come out as 25, or 5 squared. So we can again introduce normalized vectors, but just dividing by the length. And there we actually have a choice. We just need to divide by numbers which have the correct absolute value. But the easiest one is to just divide by 5. And we do this in both cases. So we get these two normalized vectors. But for instance, I could have also divided by 5 times I, or minus 5, or any kind of number that has an absolute value of 5. Okay, and then we can check, for instance, that these are indeed normalized, but this is almost too obvious, because now we have just this extra factor of 1 over 5 at every place where we multiply a component with itself. So then we have still the same sum as before. So I just do it for one case because this is obviously now 1. Now let's look at the scalar product between the two vectors, just the original ones, not the normalized ones. And now we have to take care of the complex conjugation of the first entry in the scalar product. So we take the complex conjugate of the first entry and multiply this with the first entry of the other vector. And then we do the same with the second entry. Again, a complex conjugation here and none here. And then we can multiply this out. Well, let's multiply all times out. And let's see if, well, some things cancel. All these 8 i's we can collect 2. So this would be then 20 plus 2i. So this would be the scalar product between these two different vectors. And this is just now a complex number. It doesn't vanish again, so these are not two orthogonal vectors. And now we can, of course, again introduce a vector which is orthogonal. And this is a great place to introduce the Dirac notation. So let us first translate our states into Dirac notation. And for this we now need two basis states that I'm just going to call 0 and 1. So this would be the state psi, and this is the state phi. And now we can write down a state phi prime by taking phi and subtracting the following expression. And in here, this piece just serves as our projection operator. So mathematically, this is exactly identical to what we did above with the dot products and the outer products, but this now looks like an operator. And the way that it is to be interpreted is that these two terms are being multiplied to each other. So we can also write this in the following form. Namely this form here. And there we can immediately check that this vector phi prime will be orthogonal to psi. Because if we just multiply this out with these terms, then we obtain here psi times phi, and then here we also have psi times phi, divided by psi times psi, and then multiplied by this term here. So these two cancel, and the two complex numbers there also cancel, and we just obtain 0. But we can then of course write this also concretely as our vector. So phi prime will be our original vector phi, and then we have this scalar product that we worked out, divided by the squared length of psi times the state psi itself. And then we collect all the terms in front of the 0, these terms here. And now one could check that this is indeed a vector which is orthogonal to psi, but this is already guaranteed by this construction here. One can also form the tensor product in the Dirac notation, and this is indeed very convenient because there one just applies the following rules to the basis states. So we make tensor products between basis states. And these just result into new basis states. So instead of a system which has 2 states, we now have a system that has 4 states. And when we then apply this to our states psi and phi, we can multiply everything out. So we just do this mechanically. And then you see that all the coefficients in front of these 4 states are just the products of the coefficients of the 2 vectors. So this is just identical to the original definition of this product. Notably, in these products, there is no complex conjugation. And then we can also just interpret this as a very long vector. A vector with 4 components, and the components are just as given above. So these products here. So this covers some essential parts about vector products. So let us now turn to eigenvalues and eigenvectors. And let us consider the following matrix. So what are the eigenvalues of this matrix? I can write them down immediately. And that's because I have a lot of experience with these matrices. And I will explain you how I get there, but let's first calculate the eigenvalues in the normal way. Okay, so the normal way to calculate the eigenvalues is subtract the identity matrix multiplied by a scalar from the original matrix, and then calculate the determinant of this. And this gives us here lambda squared minus 1 minus the absolute value squared of 3 plus I, so that is 3 squared and another one. And this we have to set equal to 0. And now this gives us lambda equals to the square root plus or minus of 1 plus 3 squared plus 1, so plus minus 11, which is indeed what I've written down here. Let me explain how I got there. Well, A is the Hermitian matrix, so this entry here is the complex conjugate of this entry here. And furthermore, the diagonal entries are real. And any Hermitian 2 by 2 matrix can be written in terms of 4 principal parts. A coefficient proportional to the identity matrix, which here will happen to vanish, and then coefficients in front of 3 very particular matrices, which are known as the Pauli matrices. These Pauli matrices are of the following form, and they are sort of elementary Hermitian matrices. A will be a Hermitian matrix when all the coefficients A, B, C, and D are real. In our case, they take the values 0, 3, minus 1, and 1. Written in this form, the eigenvalues of this matrix will then come out to be A plus or minus the square root of B squared plus C squared plus D squared. One way to see this is to first take the trace of A, which by definition is also the sum of the two eigenvalues. And then from this form here, we see that all these 3 matrices here have a vanishing trace, so we only get something from the identity matrix. And we get 1 from both of the diagonal entries. Let me write down this matrix for illustration. So our sum of the eigenvalues just needs to be 2A. And then we can work out the determinant of A, which on the one hand is the product of the eigenvalues, and on the other hand will come out as A squared plus B squared plus C squared plus D squared. And then we can solve these 2 equations and we will find this expression here. So working with these 2 by 2 matrices is not too complicated. Even though the off-diagonal elements might be complex numbers, we can boil everything down to real numbers. And working with 2 component vectors isn't too complicated as well. And this is the reason why quantum mechanics takes the simplest form when we talk about quantum systems that have only 2 states, so-called 2-level systems. So let us have a look at these.